Yes.
Okay, so second talk is on topic of domain adaptation for text basically, and going to be presented by Rajhans, Samdani.
All right. So I'm Rajhans. This is joint work with Scott Yee from Microsoft Research. This was work done during my internship at Microsoft Research Redmond, and the work is on domain adaptation. So let's see what it is about. So I'll have a brief overview of domain adaptation. So it's known that in case of, for example, sentiment analysis, supervised machine learning succeeds pretty well. Which is to say that if you want to do sentiment evaluation of movie reviews, supervised learning does very well. But what happens if you do use the same classifier for sentiment analysis of book reviews? It doesn't do so well. And the reason is that these are essentially different domains. And what do I mean by different domains? Well, the different domain means there are different distributions in which you are training and testing. And so the typical setting of domain adaptation is as follows. You have large amount of supervised data on one domain, but you have little to no supervised data on this another domain which you actually care about. And the idea, and the task is to use the large amount of supervised data from the first domain, which we call the source domain, to get a classifier with high accuracy on the target domain. And this problem is hugely pervasive because labeled data is very expensive. And so in this paper, we propose a technique to handle this problem. The technique is called domain adaptation with ensemble of features, or feed in short. And essentially, roughly what we do is we create an ensemble of classifiers which are trained on different groups of features. And our approach is very fast, very easy to implement, and it allows for incorporating domain knowledge about features. And at the same time, it outperforms several state-of-the-art algorithms in domain adaptation. So this is roughly the introduction, and now let's move on to the details of our talk. This is the rough outline of the talk. I'm going to talk about our approach feed. I'm going to introduce a formal problem setting, talk about something called concept drift, give the algorithm, and then generalization bound, and then we'll talk about other things. All right, so here's the formal setting. You get an example x, y, where x are the features and y is the label. And the source domain is given by a distribution ds, labeled data ls, and unlabeled data us. And for the target domain, you have distribution dt, which is actually different than the source distribution, has labeled data lt and unlabeled data ut. And the goal is to learn a labeling function for the target domain using all the data that we have. So notice that the setting which we work in is the one with small amount of labeled target data. All right. So now I'm going to introduce something which is key to our approach, and it's called concept drift. And to illustrate this thing, I'm going to use the example of email spam detection. So in email spam detection, typically you train on historical spam data, and then you test on the current data. So, but what happens with spam is that the distribution changes over time because spammers keep evolving and keep adapting to whatever spam detectors you might have. And they adapt in particular by changing the email text, hacking more computers, harvesting more user addresses, and so on and so forth. And overall, the idea is that with time, the domain changes in email spam detection, and hence there is a need for domain adaptation for spam detection. But now, the features in spam do not change uniformly. There is something more to it. So consider three different kinds of features which are used in spam detectors: email text features, sender features, and user features. Now what happens over time is that these features change distribution, but the distribution change is not the same. So text features change drastically because it's easier for spammers to change the text, but it's not so easy for them to hack new computers and harvest more user addresses. So the sender features change less drastically, or in other words, they're more reliable. So from this example, what we roughly want to generalize is as follows, that if feature group be something which is a subset of all possible features, then as domain changes, different feature groups change differently. Some feature groups change drastically, which means that they are less reliable across different domains, and some feature groups change very little, which means that their performance is more reliable across different domains. They're more predictable. And our idea is that we use these feature groups as learned units, as learned monolithic units, which have a similar cross-domain behavior. And I'll demonstrate how we actually use this idea. And I would like to note here that these feature groups can be overlapping. These feature groups don't have to be non-overlapping. In case of email, they were non-overlapping, but they can be overlapping. And we'll show experiments for everything. So now here's a primer for our algorithm based on this idea of feature group I just introduced. So what you do is, like if the domain was the same, then training a classifier on all features would be Bayes optimal. But it is actually not the case. So what our approach does is it trains classifiers on different feature groups and then essentially it reweights the feature groups to avoid learning from scratch, because you don't have enough data to learn from scratch, but you do have these compact feature group representations within which the classifier remains the same. And the feature groups can be created by either using domain knowledge, because you as domain expert know that where each feature group comes from, and there are different feature generating functions, or you can use simple ad hoc measures like mutual information and frequency to create these feature groups. And I'll show experiments with both the styles of groupings. Alright, so here is an algorithm which is very easy to understand. You're given training data ls and lt, and you're given feature groups x1 to xr. And what you want to output is a classifier which is a weighted ensemble of feature group classifiers. So alpha j is the coefficient and hj is the classifier based on feature group xj. And the algorithm is very simple. For each feature group, train a classifier hj on the based on the features using just the labeled source data. Then you fix these classifiers h1 to hr, and then you tune the coefficients alpha 1 to alpha r by minimizing some loss on that labeled target data. And once you have learned these coefficients, you retrain the classifiers on both source and target data. And that's it. You output the ensemble, which is just a weighted combination of all these classifiers. And this is our algorithm field. And we can actually present a generalization bound for this algorithm, where what we do is we bound the target error, the expected target error of the ensemble, based on the empirical target error of the ensemble on the small amount of labeled target data you had, plus the empirical source error of each feature group, as in the error of each feature group on the source data, plus a term which essentially represents the distance between two distributions. So I shall not go into the details of this generalization bound, but rough idea of this bound is that this is the ensemble coefficient of feature group, and the ensemble coefficients lets you trade off empirical target error with the source error and the distributional distances. And this gives you this extra flexibility to adapt to the new domain. So here is a description of our algorithm, and now I'm going to talk about a few related approaches, and then I'm going to distinguish those approaches from our approach. So some domain adaptation approaches use just unlabeled data to capture cross-domain behavior. So there is a work by John Blitzer, etc., where they create a latent feature representation which is supposed to generalize well to both the domains. But this algorithm is very expensive because you have to learn a large number of classifiers to capture this cross-domain behavior. And B, this algorithm is more suitable for adaptation with no target data, whereas we work in the setting where we have small amount of labeled target data. Then there is actually some work on instance reweighting approaches which reweight different instances of the source domain to make the source distribution look closer to the target distribution. But then these approaches do not perform explicit feature-based adaptation, which is something we do, and they're largely restricted to theory, and their experimental and empirical benefits are largely unknown. And then there are some approaches which use small amount of labeled target data. So there is a very popular algorithm called Easy Adapt by Haldame, which does feature replication in order to capture domain invariant and domain specific parts. Again, I'm not going into the details of this. This approach is kind of related to our approach, but it doesn't use the knowledge of similar behaving features, which is something our approach enables the user to do. And B, it's outperformed by our approach experimentally. So let's look at some experiments now. So we present experiments on sentiment analysis and spam detection. So let's consider the sentiment analysis part first. So the goal of the problem is to learn a binary sentiment classifier which, when given a text of review, can tell you whether the sentiment is positive or negative. So for example, you might want to do a sentiment analysis of book reviews using a large amount of labeled data from movie reviews, as I showed in the first slide. And this data set is pretty much a standard benchmark for domain adaptation problems and sentiment analysis problem. You have 2,000 labeled reviews for each domain, and we split it into 1,600 examples for the source and 400 other examples. Out of these 1,600 examples, we choose 160 examples as labeled target data. So overall, you have 1,600 source labeled examples, 160 labeled target examples, and you test on 400 labeled target examples. And in this case, we consider two feature groups which we create using very simple heuristics. One feature group is the total feature group, which is all the features together. As I said, the feature groups can be overlapping. And the other feature group is those features which have a high mutual information with label in the source domain and at the same time occur very frequently in the target domain. So you can use unlabeled target data to measure the frequency of words, and you can use the labeled source data, which is available in plenty, to calculate the mutual information. And then you take an intersection of these sets and obtain this feature group, which is supposed to have a good domain invariant behavior. So, and then the baselines in this case is a simple logistic regression classifier trained on the source and target data, the easy adapt approach by Haldome, and multi-view transfer approach, which is the same as structural correspondence learning approach by John Blitzer. These are both very popular domain adaptation approaches. And so I'm showing a few scatter plots here which show which algorithm is better. And these are the data points here represent each particular source target pair. So you have one target pair for books and movies, one target pair for kitchens and kitchen appliances and electronics, one target pair for DVDs and movies, yada yada yada. There are 20 such target pairs. So if all the points below the x equal to y line means that feed is better, points above the x equal to y line means easy adapt is better. So clearly, feed is doing really well in this case compared to easy adapt. Now let's compare with multi-view transfer or Blitzer. Still, feed is doing really well. And when you compare it with all data baseline, which is trained on just a simple logistic regression classifier on source and target domain, feed is still doing pretty well. But what we observe in particular in this case is that all data is a very hard baseline to defeat. Like a simple logistic regression classifier trained on source and target does pretty well. And it's consistent with the empirical wisdom which has been observed by other authors as well. And I think our approach manages to defeat all data because it's a generalization of feed. So it has the feature group which is considered by feed. On top of it, it has an extra feature group which it can tune and gain performance boost. But I guess there is no need to lose hope here at this point and say that domain adaptation doesn't work, because in the next example we show that all data doesn't work always. So the next example is of spam detection. The task setting is you want to learn a spam filter using historical spam data and apply it to messages which are received later on. So what we use are this data set by Hotmail. About 1 million messages received over some time period. 250,000 are used as labeled source data. 30,000 are used for labeled target data, and the rest are used for evaluation. And the configuration of feature, our approach as in the 3 feature groups we consider are, as we talked about initially, the features based on email text, which are the content features, the features based on sender IPs, which are the sender features, and the feature based on user information, which are the user features. So each of them has different feature generating functions, and we have this domain knowledge about this particular domain. And the baseline in this case is all data, which is logistic regression trained on all features, same as before, easy adapt algorithm. We couldn't get multi-view transfer learning to work on this case because it was too slow for this data set. The data set was just too huge for it to handle. And the evaluation metric in this case, or in case of in general spam detection, is ROC curve at low false positive rates. You really want low false positive rates because you don't want good email to be labeled as spam. You're okay otherwise. So this is the evaluation metric here. And this is the evaluation curve. Clearly we see that easy adapt is doing better than all data approach. All data is not doing so well, as you can see the ROC graph, but our approach is doing really, really well. Like, it doesn't even intersect anywhere. It's clearly better than all the other approaches, and so this shows that this approach works. And so I'll just finish with conclusions. Our approach feed is a very simple and easy to implement approach, and I hope that it will be used as a good baseline in the future and used in applications. It allows to trade off empirical target error, empirical source error, and several distributional distances by using these flexibility of ensembles. And it outperforms several popular domain adaptation algorithms, which includes SCL, multi-view transfer, both are the same, and easy adapt. And as future work, we would want to do automatic feature grouping. That is, instead of actually using heuristics-based feature groups, we would want to learn these feature groups automatically. And that's it. Thank you.